Well, hello again. Welcome. We have one more to go after this one. This is our second to last lesson for Calc BC for this year. I appreciate your guys' help, honestly. I know I say it all the time, but I really, really mean it. So we are now going to be looking at polar coordinates and polar graphs. And I know you've talked about these a little bit before, but let me show you a quick little recap of what polar graphs really are. Just remember, rectangular coordinates are coordinates along an XY grid. You go so far left, so far right. You know, here's 2, 3.5, over 2 of 3.5. You know all that fun stuff. And your coordinate is based upon how you are in an XY plane. Just like an Etch-a-Sketch. Now, when we do polar coordinates, we are finding a location in space given an angle and a radius. So notice how when I change the radius, the point gets further away. Radius is 6, it's 6 away. If I go negative, I'm just going in the opposite direction. And then the angle is my A in this case. My angle is how far I would spin. So here's 45 degrees and a radius of 3. So I am the radius of 3, actually go to 4, it's easier to see, a radius of 4 on a 45-degree angle. So a polar coordinate is a radius and an angle. And of course your angle can go all the way around. And your radius can go out or in, and remember, when it's negative, it's reversed. All right, a quick little reintroduction to polar coordinates. Okay, now the question is, how do you convert polar to rectangular and rectangular to polar? And just think about what you've got. If you've got yourself a graph, and we have a point out here, and if you think about that point, it doesn't really matter what the point is, because if you look at this little triangle right here coming off the origin, what is the relationship? Well, we know that this is an x value and that's a y value, and that's a right angle. We also know that this is an angle and that is the radius of that triangle. So in polar coordinates, we're just a radius and an angle. Rectangular coordinates are an x and a y. So what's the relationship among these? Well, one relationship is pretty obvious when you really look at it. We know x squared plus y squared will equal r squared. So that can be very helpful in converting from polar to rectangular and vice versa. We also know this angle right here. I know that the tangent of that angle equals the y over the x. So you can see, if I'm given a y and an x, can I find r and can I find theta with these two relationships? Okay. So this is one conversion. This is the easiest way to go from a rectangular to a polar, is using these. Now what about the opposite way, or thinking of another relationship here? Well, if I look at the sine of the theta angle, it's y over r. If I multiply both sides by r, I get this little relationship that y, the y value of a rectangular coordinate, is the radius times the sine of the angle. And also, if you do the cosine, you get x over r. So r cosine of theta equals x. So think about all of these. If I know r and the angle, I can get my y value, and I can get my x value. If I know x and y, I can use this to get my r value, and use this to get my angle. You just have to find the inverse tangent of that. And those come right from the graph. All right, so here we go. We're just going to take a point. We're going to take the point, now this is a polar, and it's implied in the question. I'm sorry if it's not very clear, but find the point and find the plot the point and find the corresponding rectangular coordinates for this polar coordinate. Okay. So we're making an assumption, because I just forgot to be more clear, but this is a polar form. So there's my radius and there's my angle. So I know my radius is -2 and my angle is 5 pi over 3. Alright, now the x value is the radius times the cosine of theta, and the y value is the radius times the sine of theta. Let's plug it in. My radius is -2. Remember, that's inverted. And the cosine of 5 pi over 3. So remember your unit circle stuff, and don't pretend I knew what it was. I had to look it up. But it's a half. So x value is -1. This is -2 times the sine of 5 pi over 3. And the sine of 5 pi over 3 is -√3 over 2. Multiply those together, I get -√3. So the point of -1, wow, negative times negative is positive, and positive roots of 3 should be accurate. Let's check it out. Alright, you can see here, in order to type in the polar coordinate in Desmos, I've got to put in the form of r cosine of theta and r sine of theta. And it ends up that the point is right there. When I convert it to the rectangular, I get -1 square root of 3. You'll notice that it's the exact same point. If I was to look at this on a rectangular grid, they are the exact same point. And they always will be. It doesn't matter really what grid you graph it on. Notice that you just have two choices. Alright, let's move on. Now we're going to convert this entire polar equation to rectangular form. Let's see what we know. We know that x equals r cosine of theta. Interesting, that's kind of flirting in there somewhere. We know that y equals r sine of theta. I know that x squared plus y squared equals r squared. And I also know that the tangent of theta equals y over x. Now some of these are going to be useful and some of them just totally irrelevant. The first thing I'm going to do is I'm going to multiply both sides by r. I get r squared equals r times 5 cosine of theta. Now by doing that, see how I get r cosine of theta? And what is r cosine of theta? Well, that's x. So I've taken one step. I've written that r squared equals 5x. Okay. But totally rectangular, I need to get rid of the r. Well, I also know that r squared is the same as x squared plus y squared. So, can I write x squared plus y squared equals 5x? Now, in theory, that is a correct equation. However, we're going to simplify a little bit to see if we can turn it into a form that you might recognize. It's been a long time since you've done this, equations of circles. I'm going to leave a space here. Alright. And that's 0. So I want to complete this square. Remember, go on completing the square. Half of 5 is 5 halves. And if I square it, I get 25/4. So I'm going to add 25/4 to both sides. So this becomes x minus 5 halves squared plus y squared equals 25/4. So the circle has a radius of 5 halves, because it's the square root of this, and its center is 5 halves, comma, 0. But this would be the rectangular form of that polar equation. All right, let's verify that and look at the graph. And as you can see right here, here is r5 cosine of theta on a polar coordinate, and those goes out to 5. And here's our rectangular graph, and you'll notice it's exactly the same. It's funny to me, I don't know if it's optical, well it is an optical illusion, but to me this doesn't look like it's a perfect circle, and I think it's these other concentric circles are throwing it off. Let me go to a rectangular grid. Now that looks more of a circle to me. Either way, these graphs are identical, and therefore they are equivalent. So I'm sorry I graphed all those on Desmos and not like by hand. And when you do these, if you need to graph them, you can use your calculator and just copy it down. You use Desmos, whatever you feel like. Remember, if you're using your calculator, change your mode to polar, and then you're going to get in your y equals, you're going to get r equals. You're going to see the polar form. All right, now we're going to go the other way. We're going to plot a point and find the corresponding polar coordinates for this rectangular coordinate. Again, I'm sorry I didn't make that more clear, but it is implied. This is rectangular. So I've got the point 4, -2. Well, I know where 4, -2 is. It's 4, 1, 2, 3, 4, 1, 2. It's down here. So I'm going to have an angle that's in the 4th quadrant. All right, well, here's what we know. We know that r squared equals x squared plus y squared. I know that the tangent of the angle theta is y over x. So let's solve these. X squared would be 16, and that would be 4. So r would be the square root of 20. All right, not a unit circle one right there. We might have to actually use a calculator for that. So if I put that in a calculator, inverse tangent of -2/4, I get -0.4636. And there is our polar coordinate. Now, is that correct? Let's go take a look. The point for -2 in the rectangular coordinate system, right here. And again, I have to type in the polars with the form of r cosine theta and r sine of theta. But when I do, you notice it's the exact same point. It's right there. So it's all good. We'll take a look at it in the polar coordinates. And square root of 20 is a little bit above 4. And so the radius is outside of 4. And the angle, which was -0.4636, is negative from the x-axis. There we go. Seem okay? All right, let's move on. We're going to convert this rectangular graph to a polar form. I don't know if you remember much about conic sections, but that's a hyperbola. Okay. Either way, doesn't matter. What information do we need to convert that? Well, remember this, and remember this. So I'm going to put r cosine theta squared minus r sine theta squared equals 9. I mean, technically, haven't we got rid of the x and y, and now it's all on r's and thetas? So really, this is it. But it's ugly. It can be made more simpler. It's complicated. It's not ugly. I didn't mean to say that. It can be written where it makes more sense. So I'm going to square this. Cosine squared theta. Sine squared theta. Now, I didn't remember this off the top of my head because I don't have all my trig identities memorized because it's been a while since I've actually done them. But I thought, there's got to be something for cosine squared minus sine squared. So I looked it up. I took the textbook, went right to the first page. Not even the first page, the first insert. And on the back of the first insert, it reminded me that cosine squared minus sine squared equals cosine of 2 theta. Much nicer looking, don't you think? So I'm going to divide both sides by cosine of 2 theta. And then take the square root. So we end up with, if you take the square root of both sides, 3 over the square root of cosine of 2 theta. All right, Alright, let's take a look at that graph and see what's up. Our graph of x squared minus y squared equals 9 is this hyperbola. And when I click on this little polar right here, you notice it's exactly the same. So well done. Take a look at as a polar coordinate, just so you can see. Now you might be wondering, we took the square root, why didn't we make it negative? Well, let me show you something. If I make this negative, guess what happens? Nothing. Because the negatives mean the radius switches, so this basically moved over here and this one moved over here. So nothing changed when I made it negative. So that's why I didn't make a issue out of it, because it's the same graph either way, positive or negative. Alright, how you doing? We've got one more problem to do, and it involves finding slopes of tangent lines. Now this, unfortunately, not unfortunately, it's an easy formula that looks super complicated. It's kind of like the distance formula when you first learned it. It looks really long and nasty, but it's not. It's just looks that way. So if we're doing tangent lines of polars, then our x and y values, we have to take the derivative with respect to the angle of theta. Now I want you to remember a couple things. One, that y is r sine of theta, and x is r cosine of theta. So if I took the derivative of y with respect to theta, I would get a product rule of r times the sine of theta. Okay, we're going to think of r as a function. That r is going to be some function. Now in your book, they actually used f of theta. I thought it was a little bit easier to just leave it as an r, and I'll show you why. So it's the first, and the derivative of sine is cosine. Okay, plus the derivative of r, which is r prime, times the second. So there's my derivative of y with respect to theta. And now the bottom. R, the derivative of cosine is negative sine, and chain rule, product rule, so r prime times the cosine of theta. So we'll just make it look a little nicer. Actually, the only thing we're going to do is get rid of that negative on the bottom. So we'll just say negative r sine of theta plus r prime cosine of theta. Now just so you know, if you ever look this up in your textbook and other books too, they list r as f of theta. So it says f of theta plus f prime of theta. Okay, but really this is the way I like to think about it, just because my brain is small. Alright, we're going to take this and we're going to put that over here. Alright, so remember that's what your derivative function is, or your derivative formula. So if I want to find the derivative of this polar function, so to find the derivative, and it'll be a long answer, but that's okay. It's r, so it's the whole function 3 minus 2 cosine of theta times cosine of theta plus r prime, and r prime would be negative 2, derivative of cosine is negative sine, times sine of theta. All of that over negative r times sine of theta plus r prime, which we already know is 2 sine of theta, times sine of theta. Okay? Alright, now with this in mind, let's plug in 0 for theta. Cosine of 0 is 1, so this is actually 3 minus 2 cosine of 0 is 1. Sine of 0 is 0. That's just 0 over there. Alright, this is negative 1, but we had the sine of 0, so it's actually 0. Uh-oh. We'll end up with the dreaded 1 over 0, but that's okay. They're asking for the slope of the tangent line. What's the slope when you have a non-zero divided by 0? And that's right. The slope is undefined. Let's check that out, make sure it looks good. Here's our polar graph of r equals 3 minus 2 cosine theta. You can see it's a nice little shape here that comes in a little bit of an indentation right there. We found that at the theta value of 0, which would be right along here, that this point right here has a undefined tangent line. So undefined would mean that the equation would be x equals, and so if I just pull this over, you're going to notice it is tangent right there. Oops, there we go. So when x equals 1, so if you think about when theta is 0, the radius is 1, because 3 minus 2 is 1. So at the point, at the rectangular point, I should say 1, 0, that is tangent with the rectangular equation of x equals 1. Okay, we did it. So thank you for your attention. We didn't get into a lot of the big details of the crazy pedal graphs and things like that, because really what I was worried about in this case was doing the calculus of it. So the only thing we have left in a lesson we uploaded tomorrow would be the area and length of polar coordinates. So 2 more formulas and then we are done. And we'll get that up tomorrow, so you'll have at least tomorrow, Thursday, and Friday to get everything done. Suggestion, if you haven't started yet, maybe do some of those assessment problems, get yourself up there and ready to go. All right, anyway guys, it's good seeing you. I will see you next time, and we'll go from there. All right, take it easy, bye.